Today we're going to talk about proportions and testing proportions. So I know this is everybody's favorite thing to do because we have to find proportions, probabilities, percentages, those things first before we can do it. Again, really similar to what we've done before. Confidence intervals, if you remember those, the formulas are really, really similar. So we're dealing with p hat and p. So I want you to look at, here's the z-score. Slightly different with the square root symbol. So if we're testing z-test for proportions, we do p hat minus p over the square root of pq over n. All right, and p hat is the sample proportion x over n. P is the population proportion, and n is your sample size. So again, not too difficult. You just have to know when you're dealing with proportions versus means. So let's look at an example. A statistical abstract reports that 17% of adults attend a musical play each year. To test this claim, the researcher surveyed 90 people and found that 22 had attended a musical play in the past year. At alpha equals 0.05, test the claim that this figure is correct. So basically what you're going to do is you're going to say, well, what if it's not correct? So we're going to set up, first of all, a two-tailed test. So I end up with my H naught is that the mean is equal to, or sorry, not the mean, the P is equal to, or the P hat, there's my H naught, okay. My H naught, and so I'm trying to prove that P is not equal to 0.017. My null hypothesis is that P is equal to 0.017. Okay. So, and then I look up my critical value in the chart for alpha equals 0.05 for a two-tailed test. Oh, I must have done that later. We're going to calculate P hat first. All right. So 22 over 90 P hat is 0.2444. All right, so we want to prove that that's statistically significantly different than 0.017. So Q is 0.83. Okay, my critical value, looking up in the chart now, is positive and negative 1.96. So alpha equals 0.05 with a two-tailed test. That should be familiar because that's confidence interval. My z-score, p hat minus p over the square root of pq over n. Okay. Equals 0.244 minus 0.017 over 0.17 times 0.83 over 90. Okay. Plug those all in my calculator, I get 1.88. Okay, that is not in my critical value range. Okay, I have to be bigger than 1.96 or less than negative 1.96, so I cannot reject. Okay, so this number is not statistically different than, so the 0.244 is not statistically different than 0.17, so I cannot reject. All right, now let's look at an example or practice problem. Okay, so go ahead, let's read it first. So an educator estimates that the dropout rate for seniors in high schools in Ohio is 15%. Last year, 38 seniors from a random sample of 200 Ohio seniors withdrew. At alpha equals 0.05, is there enough evidence to reject the educator's claim? Okay, again, it's going to be a two-tailed test, all right? We're trying to prove that 38 out of 20 is different than 15%. So go ahead and pause the video, do your practice problem, and then check your answer. Okay, so here's my answer. All right, so my H1, my alternative hypothesis, is that it's not equal to 0.15. My H naught is that it is. Okay, so at alpha equals 0.05, two-tailed test, critical value is 1.96. I figure out my P hat, 38 over 20 is 19, or 0.19. Okay, now this is really important. We're looking for P and Q and not P hat and Q hat, all right? So the Q comes from the P, not from the P hat, 0.05. So then I plug it into my formula, 0.19 minus 0.15 over the square root of 0.15 times 0.05 over 200 is 1.58. Again, not in my critical region, so I cannot reject. Okay, and that's it. There is no second problem today. These are all basically the same. So I will see you tomorrow.